Hello, in this lecture we'll answer two questions. In the first question, we'll find out the area of this circle that is inside square ABCD. And in the second question, we'll find out the green area, the value of the green area that is inside this quarter circle. We'll start with the first question. In the drawing, we have square ABCD. We know that angle CBT, this angle equals to 30 degrees. Line segment DP equals to 5 units. And our mission is to find out the area of this circle. So, first of all, we'll define the center of this circle as O. And we will, this point is point Q. It is the point of tendency of tangent AB with this circle. We join points O and Q together by a straight line. Point O is the center of the circle, point Q is the point of the circle itself, therefore OQ is the radius of the circle that we will define as R. We have the radius OQ that is drawn to the point of tendency, therefore according to rule number 1 that the tangent to a circle is perpendicular to the radius drawn to its point of tendency, this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. Likewise, we join points O and P together by a straight line. Point O is the center of the circle, point P is the point of the circle itself. Therefore, PO is the radius of this circle that is equal to R. And we have the radius OP that is drawn to the point of tendency, therefore according to rule number 1, this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. We know that all the angles inside the square are right angles. So all the angles inside square ABCD are right angles, so this angle equals to 90 degrees. This angle is also equal to 90 degrees. This angle is equal to 90 degrees, and finally this angle, it is also equals to 90 degrees. So actually inside quadrilateral AQPO we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of the fourth angle. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing angle must be also equal to 90 degrees. Why? Because 270 degrees plus 90 degrees is 360 degrees, that is the sum of the angles in any quadrilateral. So we found out that inside quadrilateral AQPO we have 4 right angles. Therefore, quadrilateral AQPO is a rectangle. I write it down, quadrilateral APQO is a rectangle because it has 4 right angles. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle AQPO, we get that AQ equals to PO. AQ equals to PO. But we already found out that PO equals to R. It is the radius of the circle. And from this equation, R equals to AO equals to R equals to AQ. R equals to AQ equals to PO. We derive that PO is also equals to R. PO is also equals to R. Here, PO equals to R. Again, here is actually we have here, according to the rule that the opposite sides of a rectangle are equal to each other, we get that PO equals to AQ. Again, we have PO equals to AQ according to the rule that the opposite sides of a rectangle are equal to each other. But PO equals to R, it is the radius of the circle, so PO equals to R. And from this equation, R equals to PO equals to AQ, we will derive that AQ is also equals to R. AQ equals to R. Here, AQ equals to R. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that AP equals to QO. AP equals to QO. But we have already found out that QO equals to R. It is the radius of the circle. And for this equation, AP equals to QO equals to R, we derive that AP is also equals to R. AP equals to R. Found out that AP equals to R. So actually, quadrilateral AQPO is not a rectangle but a square because of the fact that all of its sides are equal to each other, they are equal to R. We can write down that quadrilateral AQPO is a square. We also know that all the sides of a square are equal to each other, so all sides of square ABCD are equal to each other. That is to say, side AD equals to side AB. Side AD equals to side AB. AD equals to AB. What is the value of side AD? The value of side AD is 5 plus R. What is the value of side AB? The value of side AB, it is equal to R plus BQ. In conclusion, we found out that 5 plus R equals to R plus BQ. We subtract R from this equation and we get that R equals to BQ, or BQ equal, here we subtract R from this equation and we get that here R will get cancelled And we got here that 5 equals to BQ. So BQ equals to 5 units. Found out that BQ or QB equals to 5 units. In the next step, I will present to you rule number 2, and we will implement rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. So here we have the common external point, point P. From the common external point, point P, we have two tangents to the circle, tangent PA and tangent PB. According to this rule, rule number 2, the length of tangent PA equals to the length of tangent PB, or PA equals to PB. Can implement rule number 2 in our drawing. Why? Because in our drawing, if we focus on the external point, common external point, point B, from the common external point, point B, we have two tangents to this circle, tangent BQ and tangent BS. And according to rule number 2, they are equal to each other. That is to say, BQ equals to BS according to rule number 2. But we have already found out that BQ equals to 5 units, so we can write here that BQ equals to 5. And from this equation, 5 equals to BQ equals to BS, we will derive that BS is also equals to 5 units. BS equals to 5 units. And write here that BS equals to 5 units. What is the length of this angle, angle QBS? The length of angle QBS will be equal to, what is the size of angle QBS? The size of angle QBS will be equal to the size of angle ABC, the big angle, minus the size of angle TBC. That is to say, it will be equal to the size of angle ABC, that is 90 degrees, minus the size of angle TBC, that is 30 degrees. 90 degrees minus 30 degrees, it is equal to 60 degrees. So this angle, angle QBS equals to 60 degrees. The next step, we will join points Q and S together by a straight line. Here, by joining points Q and S, we created here triangle QBS. In triangle QBS, those two sides are both equal to 5 degrees, therefore they are equal to each other. 5 units, therefore they are equal to each other. That is to say, side QB equals to side BS. And we have the rule that in front of equal sides in the triangle, there are equal angles. So those two angles that are located in front of the equal sides must be equal to each other. So if this angle equals to alpha, then this angle must be also equal to alpha, because of the fact that those two angles are equal to each other. Okay, so both those two angles are equal to alpha. We focus on triangle QSB. In triangle QSB, this angle equals to 60 degrees, Therefore, the sum of the other two angles must be equal to 180 degrees minus 60 degrees. That is to say, the sum of those two angles that are alpha and alpha must be equal to 180 degrees minus 60 degrees is 120 degrees. That is to say, alpha plus alpha equals to 120 degrees. Make it clear that we found out that alpha plus alpha must be equal to 120 degrees. Alpha plus alpha is 2 alpha, so 2 alpha equals to 120 degrees. Here we divide this equation by 2, and you get that angle alpha equals to 120 degrees over 2 is 60 degrees. So we found out that angle alpha equals to 60 degrees. Here, this is angle alpha that is equal to 60 degrees. And this is also angle alpha that is equal to 60 degrees. So in triangle BQS, this triangle, we have three angles that are equal to 60 degrees. Therefore, triangle QBS is an equilateral triangle. I will write it down. Triangle QBS is an equilateral triangle. Why? Because it has three angles that are all equal to 60 degrees. And we know that in an equilateral triangle, all the sides must be equal to each other. So in this equilateral triangle, QB equals to 5, BS equals to 5, therefore the missing side, the third side, that is to say side QS, must be also equal to 5 units. So we found out that QS equals to 5 units. In the next step, we will join points O and S together by a straight line. Point O is the center of the circle. Point S is the point of the circle itself. Therefore, OS is the radius of the circle that is equal to R. Okay. In the next step, I will copy quadrilateral OSQB in a new page and we will analyze this quadrilateral SOQB. Okay. So actually, this is quadrilateral QBOS that I copied from the original drawing. This quadrilateral, this is the missing angle. Angle QOS is the missing angle. And we know that the sum of the angles in any quadrilateral is equal to 360 degrees. That is to say, the size of the missing angle, that is to say angle QOS, will be equal to 360 degrees minus the sum of the other three angles. That is to say, it is 360 degrees minus 90 degrees plus 90 degrees plus 60 degrees. So the missing angle, angle QOS, will be equal to 360 degrees minus 90 degrees plus 90 degrees is 180 degrees. 180 degrees plus 60 degrees it is 240 degrees. So the missing angle equals to 360 degrees minus 240 degrees, it is 120 degrees. So we found out that the size of the missing angle, angle QOS, equals to 120 degrees. So this angle equals to 120 degrees. So in the next step, I will present to you the law of cosines, and we will implement the law of cosines in the green triangle, triangle QOS. So what is the law of cosines? The law of cosines is true in any triangle. So if we have triangle ABC that could be any triangle, this is triangle ABC. The length of side AB is A units, the length of side AC is B units, and the side BC equals to C units in its length, and the angle between side AB and side AC is theta. So in this triangle, triangle ABC, we will get that, according to the law of cosines, we will get here that C square equals to A square plus B square minus 2 times A times B times cosine theta. Again, C square equals to A square plus B square minus 2 times A times B times cosine theta. Now we will implement the law of cosines in the green triangle, triangle QOS. So I'll copy triangle QOS in a new page, and we'll implement the law of cosines in triangle QOS. So this is actually triangle QoS that they call it from the original drawing. So according to the law of cosines, we get that in triangle QoS 5 squared equals to r squared plus r squared minus 2 times r times cosine 120 degrees. Five squared is 25. That is equal to r squared plus r squared is 2r squared minus 2 times r is minus 2r squared times cosine 120 degrees. Here cosine 120 degrees equals to minus 1/2 times 2r squared so we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. Minus times minus is plus, so in conclusion we found out that 25 equals to 2r squared plus r squared. So 25 equals to 2r squared plus r squared is 3r squared. Here we'll divide this equation by 3 and we'll get that r squared equals to 25 over 3. And the area of a circle, the area of any circle is equal to pi r squared. The area of our specific circle will be also equal to pi r squared. But we have already found out that r squared equals to 25 over 3, so we'll substitute r squared in this formula by 25 over 3, and we get that the area of our circle will be equal to pi times r squared, and r squared is 25 over 3. So in conclusion, we found out that the area that we are looking for, the area of the circle, equals to either 25 pi over 3 square units, or in terms of numbers it is equal to 50.265 square units. Okay. Again, the area of this circle equals to either 25 pi over 3, or in terms of numbers it is equal to 50.265 square units. We finished with the first question. In the next step I'll present to you the second question, and we'll solve the second question in 3 different methods. In the drawing we have a quarter circle. Inside this quarter circle we have a small circle. We know that line segment CD equals to 8 units, angle ACD equals to 90 degrees, and our mission is to find out the area of the green shape. Okay. So we start with the first method. In the first method, we will define the center of the small circle as J. We define the point of tendency D with this small circle as E. We define the point of tendency of tangent OB with the small circle as F. We join points J and D together by a straight line. Point J is the center of the small circle, point E is the point of the small circle itself, therefore EJ is the radius of the small circle that we will define as R. And we have the radius JE that is drawn to the point of tendency, therefore according to rule number 1, this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. Likewise, we join points G and F together by a straight line. Point J is the center of the small circle, point F is the point of the small circle itself, therefore JF is the radius of the small circle that is equal to R. We have the radius JF that is drawn to the point of tendency, therefore according to rule number 1, this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. Because of the fact that this is a quarter circle, point O must be the center of the quarter circle, and this angle COB, must be equal to 90 degrees. It is true in any quarter circle. In addition, AO must be the radius of the quarter circle that we will define as capital R. So here AO as a radius, it must be a straight line. So if we focus on this side of the straight line AO at point C, here the sum of the angles must be equal to 180 degrees according to rule number 3. So which angles we have at this side of the straight line AO at point C, we have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees. Therefore, the missing angle must be also equal to 90 degrees in order to complete the sum of the angles on this side of the straight line AO at point C to 180 degrees. This angle must be equal to 90 degrees. Okay, so in the next step, from point J, that is the center of the small circle, we will draw perpendicular on CO. So this angle equals to 90 degrees and this angle will be also equal to 90 degrees according to our construction. We will define the touching point of the perpendicular from point J and CO as T. So actually, inside quadrilateral CEJT, we have 1, 2, 3 right angles. The sum of right angles is 270 degrees. Therefore, the fourth angle must be also equal to 90 degrees. In order to complete the sum of the angles in this quadrilateral to 360 degrees, this angle must be also equal to 90 degrees. Likewise, in quadrilateral TJOF, we have 1, 2 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Okay, so we found out that this angle EJF, it is equal to 90 degrees plus 90 degrees, that is 180 degrees. Therefore, angle EJF, it is a straight line. If angle EJF is a straight line, then line segment EJF is a straight line, and if line segment EJF is a straight line, it means that line segment EF is also a straight line. Line segment EF is a straight line. And if line segment EF is a straight line, it means that quadrilateral CEOF, this quadrilateral, is a rectangle. I write it down. Quadrilateral CEOF is a rectangle. Why? Because it has 4 right angles. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, EF equals to CO. EF equals to CO. But we already found out that EF equals to R plus R, that is 2R. So we can write here that EF equals to 2R. And for this equation, 2R equals to EF equals to CO. We will derive that CO is also equals to 2R. CO equals to 2R. CO equals to 2R. Okay. And in the next step, we join points O and D together by a straight line. Point O is the center of the circle, point D is the point of the circle itself, therefore OD. Point O in the center of the quarter circle, point D is the point of the quarter circle itself, therefore OD is the radius of the quarter circle, that is equal to capital R. In the next step, we will implement the Pythagoras theorem on the right green triangle, triangle OCD. In the right green triangle, triangle OCD, by PT is a version for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle COD is OD, therefore the square of the hypotenuse is OD squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to CO squared plus CD squared. I repeat again, in the right green triangle, triangle OCD, according to the Pythagoras theorem, OD squared equals to CO squared plus CD squared. OD, the hypotenuse OD equals to capital R, therefore OD squared is capital R squared. That is equal to CO squared. CO equals to 2R, therefore CO squared is 2R squared, that is 4R squared. Plus CD squared. CD is 8, so CD squared is 8 squared, that is 64. So according to equation number 1, we found out that capital R squared equals to 4R squared plus 64. We subtract 4R squared from this equation, equation number 1, and we get that according to equation number 1, capital R squared minus 4R squared equals to 64. Okay. And what is actually the area of the green shape? For the drawing, it is very easy to see that the area of the green shape equals to the area of the quarter circle minus the area of the small circle. I repeat again, the area of the ring shape equals to the area of the quarter circle minus the area of the small circle. So the area of the quarter circle will be equal to pi times capital R square over 4 minus the area of the circle, that is pi R square. So I found out that the area of the ring shape equals to pi times capital R square over 4 minus pi R square. Here we take pi over 4 as a common factor out of those two expressions. So here what is left from pi R square over 4 after we go from it pi over 4 as a common factor, what is left is actually capital R square. And what is left from minus pi R square after we took from it pi over 4 as a common factor, what is left is actually minus 4 R square. Why? Because minus 4 R square times pi over 4 it is equal exactly to minus pi R square. Okay, so I found out that the area of the ring shape equals to pi over 4 times capital R square minus 4 R square. But this expression, capital R square minus 4 R square, found out that capital R square minus 4 R square according to equation number 1 equals to 64. Therefore we can substitute capital R square minus 4 R square by 64. We'll do it now and get that the area of the ring shape will be equal to pi over 4 times 64. 64 over 4 is 16. So in total this expression equals to 16 pi. So we found out that the area of the ring shape equals to either 16 pi square units, or in terms of numbers it is equal to 50.265 square units. Okay, we finished with the first method. In the next step I present to you how to find out the area of this ring shape according to the second method. In the second method we use before the things that we already found out in the first method. We already found out that CO equals to 2R. We have already found out that AO is the radius of the quarter circle that is equal to capital R. What is the value of AC? Here AC equals to AO minus CO. AO minus CO. Again, AC equals to AO minus CO. So AC equals to AO, that is capital R, minus CO, that is 2R. So in conclusion, we found out that AC equals to capital R minus 2R. This is the radius of the small circle that is equal to R, and this is also the radius of the small circle that is equal to R. Okay. We already found out that this angle equals to 90 degrees. Only for rule number 3. This again it is also equal to 90 degrees. In the next step we will complete the quarter circle to a circle. So we completed the quarter circle to a circle. We'll extend the radius AO by a straight line until it intersects with the circle. We'll define the intersection point or the touching point of the extended radius AO and the circle is T. So point O is the center of the circle, point T is the point of the big circle itself, therefore OT is the radius of the big circle that is equal to capital R. In the next step, we'll extend the radius the straight line CD by a straight line until it intersects with the circle, and we will define the touching point of the extended straight line CD and the circle as point M. We will join points O and M together by a straight line. Point O is the center of the big circle, point M is the point of the big circle itself, therefore OM is the radius of the big circle that is equal to capital R. We join points O and D together by a straight line. Point O is the center of the big circle, point D is the point of the big circle itself, therefore OD is the radius of the big circle that is equal to capital R. Actually, we extended the straight line DC by a straight line. When you extend a straight line by a straight line, the result must be a straight line. Therefore, here DM must be a straight line. So if you focus on the lower side of the straight line DM at point C, here the sum of the angles must be equal to 180 degrees according to rule number 3. So which angles we have at the lower side of MD at point C? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees according to rule number 3. Therefore, the missing angle here must be equal to 90 degrees. In order to complete the sum of the angles in the lower side of MD at point C to 180 degrees, this angle must be equal to 90 degrees. So actually we created here two right angles. The right angle CMO and the right angle CDO. We prove that those two right angles can go into each other. So I write it down. We prove that the right triangle MCO is congruent to the right triangle CDO. So why those two right triangles can go into each other? First of all, CO is the current side that belongs to both triangles, so CO equals to itself. It's the current side that belongs to both triangles. In addition, MO equals to OD, they are both the radii of the big circle, therefore they are equal to each other. MO equals to OD, they are both equal to capital R, therefore they are equal to each other. So actually by proving that the hypotenuse and one perpendicular of those two right triangles congruent, we prove that those two right triangles congruent to each other. I'm explaining why. Because if, for example, we have two right triangles, we have the right triangle, triangle ABC, that's congruent to the right triangle, triangle EDF. This is triangle ABC. And this is triangle DEF. Here, the hypotenuse AC equals to the hypotenuse EF. They are both equal to 5 units, therefore they are equal to each other. The perpendicular AB equals to the perpendicular DE. They are both equal to 4 units, therefore they are equal to each other. So if we have the hypotenuse and one perpendicular that's congruent here, the third side must be also congruent. According to the Pythagoras theorem, the value of BC will be equal to the square root of 5 squared minus square root of 4 squared. 5 squared is 25, minus 4 squared is 16, 25 minus 16 is 9, and the square root of 9 is 3. Likewise, here, the value of the side EF will be also equal to 5, the square root of 5 squared minus 4 squared, that is 3. So we actually found out here that if we have in two right triangles the hypotenuse and the perpendicular congruent, then the first side must also congruent. Therefore, you can say that those two right triangles here and here also, they congruent to each other according to side rule. Okay, I can derive from what we explained here that the right triangle, triangle MCO, congruent to the right triangle, triangle COD, according to side rule. And from the fact that those two right triangles congruent to each other, we will derive that side DC equals to side CM. Side DC equals to side CM according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the two corresponding sides, that is to say DC and CM, must be also equal to each other. But it is given as the equation DC equals to 8. So from this equation 8 equals to DC equals to CM, we derive that CM is also equals to 8. CM equals to 8 units. So in the next step, I will present to you rule number 11 and we will implement rule number 11 in our drawing. According to rule number 11, if chord AB intersects with chord CD at point O, then the following equation is true that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we actually can implement rule number 11 in our drawing, because in our drawing we have chord AT that intersects with chord MD at point C. Chord AT intersects with chord MD at point C. I write it down in our drawing. We have chord AD here chord AT intersects with chord MD at point C. Point C is the intersection point. Repeat again. Chord AT intersects with chord MD at point C. Therefore, according to rule number 11, we get that MC times CD equals to AC times CT. Again, MC times CD equals to AC times CT. I write it down. MC times CD equals to AC times CT. Repeat again. According to rule number 11, we get that MC times CD equals to AC times CT. Okay. MC equals to 8, CD also equals to 8, so MC times CD is 8 times 8, that is 64. That is equal to AC. AC is capital R minus 2R times CT. CT equals to 2R plus capital R. So in conclusion, we found out that according to rule number 11, 64 equals to capital R minus 2R times capital R plus 2R, or 64 equals to capital R plus 2R times capital R minus 2R. We have the trigonometric and the algebraic identity that A plus B times A minus B equals to A squared minus B squared. Okay. And now a specific expression, A equals to capital R and B equals to 2R. So we get that according to the algebraic identity, A plus B times A minus B equals to A squared minus B squared. So this expression will be equal to A squared. A is R, so A squared is R squared, capital R squared, minus B squared. B is 2R, so minus B squared will be equal to minus 2R squared. So in conclusion, we found out that 64 equals to capital R squared minus 2R squared is minus 4R squared. In conclusion, we found out that 64 equals to capital R squared minus 4R squared. But what is actually the area of the green shape? The area of the green shape will be equal to the area of the quarter circle minus the area of the small circle. Repeat again. The area of the green shape equals to the area of the quarter circle minus the area of the small circle. So the area of the quarter circle, we have only found it in method 1. It is equal to pi times capital R square over 4 minus the area of the small circle, that is pi R square. Here we took pi over 4 as a common factor, so inside the brackets we left only with capital R square minus 4R square, and here capital R square minus 4R square, it is equal to 64 according to this equation. So we substitute capital R square minus 4R square by 64 and get that the area of the green shape will be equal to pi over 4 times 64. 64 over 4 is 16. So in total this expression equals to 16 pi. So the area of the green shape equals to either 16 pi square units, or in terms of numbers it is equal to 50.26 pi square units. So we finish with the second method. In the next step I present to you how to find out the area of this green shape according to the third method. We already found out that CO equals to 2R, AO equals to capital R, it is the radius of the quarter circle. We have already found out that AC equals to capital R minus 2R. We have already found out that this angle equals to 90 degrees. This angle it is also equals to 90 degrees. This is the radius of the small circle. This is also the radius of the small circle. In the next step, we'll complete the quarter circle to a semicircle. We completed the quarter circle to a semicircle. We will extend the radius AO by straight line until it intersects with the semicircle. We define the touching point of the intersection point as T. So here, point O is the center of the big circle, point T is the point of the big circle itself, therefore T is the radius of the big circle, that is equal to capital R. So we extended the radius AO, that is a straight line by straight line. When you extend a straight line by straight line, the result is a straight line. That is to say, AT is a straight line. AT as a straight line, it is actually chord. We have chord AT in this semicircle that is equal to 2 times capital R and passes for the center of the semicircle. Okay, so because of the fact that chord AT is equal to 2 times capital R and passes for the center of the semicircle, that is to say for point O, AT must be the diameter of the semicircle. I'll write it down. AT, that is equal to 2R, it is the diameter of the semicircle. the next step, we join points T and D together by straight line. We join points A and D together by straight line. So created here peripheral angle ADT that rests on AT, that is the diameter of the circle. Therefore, peripheral angle ADT that rests on the diameter of the circle must be equal to 90 degrees according to rule number 5. Any peripheral angle that rests on the diameter of a circle or semicircle must be equal to 90 degrees. Here we have peripheral angle AB that rests on AB, that is the diameter of the circle. Therefore, peripheral angle AB equals to 90 degrees. And implement rule number 5 in our drawing. For the our drawing, we have peripheral angle ADT that rests on AT, that is the diameter of the circle. Therefore, peripheral angle ADT will be equal to 90 degrees. We define angle ATD as alpha and angle TAD as beta. We'll focus on the right triangle, triangle ADT. In the right triangle, triangle ADT, this angle equals to 90 degrees. Therefore, the other two angles must be also equal. The sum of the other two angles must be also 90 degrees. Because of the fact that the sum of the angles in any triangle is 180 degrees. That is to say, alpha plus beta must be equal to 90 degrees. Alpha plus beta equals to 90 degrees. We will subtract alpha from this equation and we get that beta equals to 90 degrees minus alpha. We subtract beta from this equation and we get that alpha equals to 90 degrees minus beta. We will focus on the right triangle ADC. In the right triangle ADC, this angle equals to 90 degrees, this angle equals to beta. Therefore, the missing angle must be equal to 90 degrees minus beta, because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees minus 90 degrees plus 90 degrees is 180 degrees. This is the sum of the angles in any triangle. So this angle must be equal to 90 degrees minus beta. We already found out that 90 degrees minus beta equals to alpha. Therefore, we can substitute 90 degrees minus beta by alpha here. Likewise, we focus on the right triangle, triangle CDT. In the right triangle, triangle CDT, this angle equals to 90 degrees, this angle equals to alpha. Therefore, this angle must be equal to 90 degrees minus alpha. But we already found out that 90 degrees minus alpha equals to beta. So we can substitute 90 degrees minus alpha by beta here. In the next step, we will prove that the right triangle ACD, the right green triangle, is similar to the right triangle CDT. Okay, so I write it down. We will prove that the right triangle ADC is similar to the right triangle CDT. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. So here, angle ADC equals to angle CTD. They are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to beta, therefore they are equal to each other. So angle CAD is equal to this angle, angle CDT. They are both equal to beta, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, therefore they are equal to each other. So angle ACD is equal to this angle, that is actually angle TCD. They are both equal to 90 degrees, therefore they are equal to each other. So I actually found out that those two right triangles are similar to each other according to angle similarity rule. Triangle ADC is similar to triangle CDT according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We will derive that AC in triangle ACD over CD in triangle CDT is equal to CD in triangle ACD over CT in triangle CDT. I repeat again, we derive that AC over CD equals to CD over CT. Okay. AC equals to capital R minus 2R. CD is 8. What is the value of CT? CT equals to 2R plus capital R. So in conclusion, according to equation number 1, we found out that capital R minus 2R over 8 equals to 8 over capital R plus 2R. Here we post multiply this equation number 1, and we get that according to equation number 1, 8 times 8 is 64, and it is equal to capital R plus 2R times capital R minus 2R. So 64 equals to capital R plus 2R times capital R minus 2R. We already found out that it is equal to capital R squared minus 4R squared. Okay. So in conclusion, we found out that according to equation number 1, 64 equals to capital R squared minus 4R squared. But what is the area of the green shape? The area of the green shape it is equal actually to the area of the quarter circle minus the area of the small circle. Repeat again. The area of the green shape equals to the area of the quarter circle minus the area of the small circle. So here we have already found out that the area of the quarter circle is pi times capital R square over 4. We already found out that the area of the small circle equals to pi R square. Here we took pi over 4 as a common factor out of those two expressions. So in the brackets we have here capital R square minus 4R square. We already found out that capital R square minus 4R square equals to 64. So let's substitute this expression by 64 and we get that the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16. So in total this expression equals to 16 pi. So the area of the green shape equals to either 16 pi square units, or in terms of numbers it is equal to 50.265 square units. So we finished with the second question. In the next step I will summarize the lecture. We start with the first question, of course. In the drawing, we have square ABCD. Inside square ABCD, we have a circle. Angle CBD equals to 30 degrees. Line segment DP equals to 5 units. And our mission is to find out the area of this circle. We define the center of this circle as O. QO is the radius of this circle that is drawn to the point of tendency. Therefore this angle equals to 90 degrees and this angle equals to 90 degrees. According to rule number 1. OP is the radius of this circle that is drawn to the point of tendency. Therefore according to rule number 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. We know that all the angles inside square ABCD are right angles, so this angle equals to 90 degrees. All the rest angles are all equal to 90 degrees, of course. So inside quadrangle AQPO, we have 1, 2, 3 right angles. And we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. Therefore, the fourth angle must be also equal to 90 degrees. So inside quadrangle AQPO, we have 4 right angles. And we know that the opposite sides, therefore, quadrangle AQPO is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, PO equals to AQ. PO equals to AQ, but PO equals to R. It is the radius of the circle. And from this equation, R equals to PO equals to AQ, we derive that AQ is also equals to R. Here AQ equals to R. Likewise, according to the sum rule that the opposite sides of a rectangle are equal to each other, we get that AP equals to QO, but QO equals to R. And from this equation, AP equals to OQ equals to R, we derive that AP is also equals to R. Here, AP is also equals to R. So we found out that quadrangle AQPO is not a rectangle but a square because all of its sides are equal to R. Then we know that all the sides of a square are equal to each other. So in square ABCD, side AD equals to side AB. AD equals to here. AD equals to AB in square ABCD. What is the value of AD? AD equals to R plus 5. What is the value of AB? AB equals to R plus QB. In total, we found out that 5 plus R equals to R plus QB. We subtracted R from this equation and found out that QB equals to 5. Yes, QB equals to 5. Then I presented to you rule number 2. And we implemented rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from common external point to a circle are equal. We have the common external point P. From the common external point P, we have tangent PA and tangent PB. And according to rule number 2, PA equals to PB. We can implement PA equals to PB. We can implement rule number 2 in our drawing. But in our drawing, if we focus on the common external point B, from the common external point B, we have tangent BQ and tangent BS. And according to rule number 2, they are equal to each other. That is to say, here the common external point B, BQ equals to BS according to rule number 2, but we have already found out that BQ equals to 5, so from this equation 5 equals to BQ equals to BS, we derive that BS is also equals to 5. Here BS equals to 5. Okay, then what is the value of this angle? The value of this angle is 90 degrees minus 40 degrees, that is 60 degrees. Then we join points Q and S together by a straight line. So here we created triangle QSB, triangle QSB. Those two sides are both equal to 5 units, therefore they are equal to each other. We have the rule that in front of equal sides in the triangle, there are equal angles. So in front of those two sides, we have those two angles that must be equal to each other. So if one angle is alpha, then the other angle must be also equal to alpha. So those two angles, they are both equal to alpha. So this angle equals to 60 degrees. Therefore, the sum of the two other angles must be equal to 180 degrees minus 60 degrees, which is 120 degrees. That is to say, alpha plus alpha must be equal to 120 degrees. Alpha plus alpha equals to 120 degrees. Alpha plus alpha is 2 alpha, that is equal to 120 degrees. We divided this equation by 2 and found out that angle alpha equals to 120 degrees over 2, that is 60 degrees. So those two angles are equal to 60 degrees. So in triangle QBS, we have all angles are equal to 60 degrees, therefore triangle PQS is an equilateral triangle. And we know that all the sides of an equilateral triangle are equal to each other, so QB equals to 5, BS equals to 5, therefore the missing side QS must be also equal to 5. Then we join points S and O together by a straight line. Point O is the center of the circle, point S is the point of the circle itself, therefore OS is the radius of this circle that is equal to R. We have the radius OS that is drawn to the point of tendency. Therefore, here, according to rule number 1, this angle equals to 90 degrees, and this angle it is also equal to 90 degrees. Then I copy quadrangle QS B QOSB in a new page and we analyze triangle QBOS. This is a quadrangle QBOS that I copied from the original drawing. Those two angles are right angles. This angle equals to 60 degrees. Angle QOS is the missing angle. We know that the sum of the angles in quadrangle QBOS is 360 degrees. So 360 degrees minus the sum of those three angles must be equal to the size of the fourth angle. That is to say, the missing angle SOQ must be equal to 360 degrees minus the sum of the three known angles. That is 90 degrees plus 90 degrees plus 60 degrees, that is 240 degrees. So in conclusion, we found out that the value of the missing angle is 360 degrees minus 240 degrees, that is 120 degrees. Angle SOQ equals to 120 degrees. So this angle SOQ is equal to 120 degrees. Then I presented to you the law of cosines and we implemented the law of cosines in this plane triangle, triangle QOS. According to the law of cosines, if we have triangle ABC that could be any triangle, Here side AB equals to A units, side AC equals to B units, and side BC equals to C units. It's left, and the angle between side AB and side AC is theta. Then according to the law of cosines, we get that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Implemented the law of cosines in triangle QOS. In triangle QOS, according to the law of cosines, we get that 5 squared equals to R squared plus R squared minus 2 times R times cosine 120 degrees. Okay, so 5 squared is 25, R squared plus R squared is 2R squared, minus 2R times R is minus 2R squared, cosine 120 degrees is minus 1 half. So we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. Minus times minus is plus. So we found out that 25 equals to 2R squared plus R squared, that is 3R squared. So 25 equals to 3R squared. We divided this equation by 3 and found out that R squared equals to 25 over 3. R squared equals to 25 over 3. We know that the area of any circle is pi r squared. The area of our circle is also equals to pi r squared. We already found out that r squared equals to 25 over 3, so we can substitute r squared in this formula by 25 over 3. We did it when we got that the area of our circle equals to pi times r squared. R squared is 25 over 3. So in conclusion, we found out that the area of our circle is either 25 pi over 3 square units, or in terms of numbers, it is equal to 50.265 square units. The area of the circle equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. We finished with the first question, then I presented to you the second question, and we solved the second question in 3 different methods. So in the drawing, we have a quarter circle. Inside this quarter circle, we have a small circle. Line 7 CD equals to 8 units. Angle ACD equals to 90 degrees. And our mission is to find out the area of the green shape. We define the center of this small circle as J. JE is the radius that is drawn to the point of tendency. This angle equals to 90 degrees, and this angle equals to 90 degrees according to rule number 1. JF is the radius of the small circle that is drawn to the point of tendency. Therefore, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. We know that this is a quarter circle, therefore this angle equals to 90 degrees. Point O is the center of the quarter circle, and AO is the radius of the quarter circle that is equal to capital R according to our definition. AO is a radius, it is absolutely a straight line. So if you focus on this side of the straight line AO at point C, here the sum of the angles must be equal to 180 degrees. So this angle equals to 90 degrees, therefore the missing angle must be also equal to 90 degrees according to rule number 3. Then for point J, that is the center of the small circle, we draw perpendicular on CO. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point J and CO as T. So in quadrilateral CETJ, the small quadrilateral, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. In quadrilateral TJFO, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Okay, so here we found out that here this is the fourth angle that must be also equal to 90 degrees. So we found out that angle EFG equals to 90 degrees plus 90 degrees, that is 180 degrees. Therefore, angle EFG is a straight, angle EJF is a straight line. Therefore, EFJ is a straight line, and therefore EF is also a straight line. So if EF is a straight line, it means that quadrilateral CEOF is a rectangle. Why? Because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say, EF equals to CO. EF equals to 0, but we have already found out that EF equals to R plus R, that is 2R. And for this equation, 2R equals to EF equals to CO, we will derive that CO is also equals to 2R. Here, CO equals to 2R. Then we join points O and D together by set line. Point O is the center of the quarter circle, point D is the point of the quarter circle itself, therefore OD is the radius of the quarter circle, that is equal to capital R. Then we implemented the Pythagoras theorem on the right green triangle, triangle COD. According to the Pythagoras theorem, OD square equals to CO square plus CD square. Here, OD square equals to CO square plus CD square. OD is capital R, therefore OD square is capital R square. CO is 2R, therefore CO square is 2R square, that is 4R square, plus CD square. CD is 8, so CD square is 8 square, that is 64. So in conclusion, we found out that according to equation number 1, capital R square equals to 4R square plus 64. We subtracted 4R square from this equation and found out that capital R square minus 4R square equals to 64 according to equation number 1. What is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. Again, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. The area of the quarter circle is pi times capital R over 4 minus the area of the circle, that is pi R squared. We took pi over 4 as a common factor out of those two expressions, so what is left from pi times capital R squared over 4 after we took from it pi over 4 as a common factor? What is left is actually capital R squared. What is left from minus pi times R squared after we took from it pi over 4 as a common factor? What is left is actually minus 4R squared. Why? Because minus 4R squared times pi over 4 is exactly minus pi R squared. So here capital R square minus 4R square, but we already found that capital R square minus 4R square equals to 64, therefore we can substitute capital R square minus 4R square by 64. We did it, and we got that the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16, so in total this expression equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. We finished with the first method. Then I presented to you how to find out the area of the green shape according to the second method. In the second method, we have already found out that in the first method that CO equals to 2R, here OA is the radius of the quarter circle that is equal to capital R. What is the value of AC? AC equals to AO times minus CO. Again, AC equals to AO minus CO. AC equals to AO minus CO. So AC equals to AO, that is capital R, minus CO, that is 2R. So in conclusion, we found out that AC equals to capital R minus 2R. This angle equals to 90 degrees according to the first method, and we completed the quarter circle to a circle. We extended the radius AO by set line until it touches the circle at point T. Point O is the center of the big circle, point T is the point of the big circle itself, therefore OT is the radius of the big circle, that is equal to capital R. We extended the straight line DC by straight line until it touches the circle at point M. When you extend the straight line by straight line, the result is a straight line. So DM is a straight line. If we focus on the lower side of the straight line DM at point C, here the sum of the angles must be equal to 180 degrees. So which angles we have at the lower side of DM at point C? We have this angle that is equal to 90 degrees plus the sum plus this angle. In total they must be equal to 180 degrees according to rule number 3. So the missing angle must be also equal to 90 degrees in order to complete the sum of the angles on the lower side of DM at point C to 180 degrees. This angle must be equal to 90 degrees. So we have here two right triangles, triangle MOC and triangle DCO. We proved that those two right triangles can go into each other. why they can go into each other. First of all, CO is a common side that belongs to both triangles, and we have MO equals to OD. They are both the radii of the big circle, therefore they are equal to each other. I repeat again. Here, CO equals to CO is a common side, and MO equals to OD. They are both the radii of the big circle, therefore they are equal to each other. By proving that the hypotenuse and one perpendicular in those two right triangles congruent, we prove that those two right triangles congruent to each other. Why? Because if, for example, we have two right triangles, in these two right triangles, the hypotenuse and one side congruent. Why? Because AC equals to EF equals to 5 and AB equals to EF equals to 4. Therefore, the third side must also congruent. Why? Because the third side, according to the Pythagoras theorem, must be equal to the square root of 5 1 square root of 4, that is 3. So in this way, I prove to you that if we have the hypotenuse and one perpendicular that is congruent in two right triangles, then the third side must also congruent. Therefore, you can say that those two right triangles congruent to each other according to side rule. Why? Because we have the hypotenuse and one perpendicular that congruent, therefore the third side must also congruent, and therefore those two triangles congruent to each other according to side rule. From the fact that those two triangles congruent to each other, we derive that DC equals to CM according to the rule that corresponding sides of congruent triangles are equal to each other. But DC equals to 8 according to what's given as equation. So from this equation 8 equals to DC equals to CM, we derive that CM is also equals to 8. Here, CM also equals to 8. Then I presented to you rule number 11, and we implemented rule number 11 in our drawing. According to rule number 11, if we have chord AB that intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. You can implement rule number 11 in our drawing, because in our drawing we have chord AT that intersects with chord MD at point C. Therefore, according to rule number 11, we get that MC times CD equals to AC times CT. Again, chord AT intersects with chord MD at point C. Therefore, according to rule number 11, MC times CD equals to AC times CT. Here MC is 8, CD is 8, so 8 times 8 is 64. AC is capital R minus 2R, CT is capital R plus 2R. So in conclusion, we found out that 64 equals to capital R plus 2R times capital R minus 2R. We've already found out that this expression equals to capital R squared minus 2R squared. So in conclusion, we found out that 64 equals to capital R squared minus 2R squared. 64 equals to capital R squared minus 4R squared. And what is the area of the green shape? The area of the green shape will be equal to the area of the quarter circle minus the area of the small circle. We've already found out that the area of the quarter circle is pi times capital R squared over 4, the area of the small circle is pi R squared. Then we took pi over 4 as a common factor from those two expressions, so inside the brackets we left only with capital R squared minus 4R squared. But this expression equals to 64, so we can substitute this expression by 64. We did it and we got that the green area equals to pi over 4 times 64. 64 over 4 is 16, so in total this expression equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers it is equal to 50.265 square units. We finished with the second method, and I presented to you how to find out the area of the green shape according to the third method. In the third method, we know that from the first method the CO equals to 2R. This angle equals to 90 degrees from the first method. This angle also equals to 90 degrees. AO is the radius of the quarter circle that is equal to capital R. We have already found out that AC equals to capital R minus 2R. So we extended the quarter circle, we completed the quarter circle to a semicircle. Then we extended the radius AO until it touches the semicircle at point T. Point O is the center of the quarter circle. Point T is the point of the point O is the center of the semicircle. Point T is the point on the semicircle itself. Therefore, OT is the radius of the semicircle that is equal to capital R. We extended AO, that is a straight line by straight line. When you extend a straight line by straight line, the result is a straight line. So AT is a straight line that is equal to 2 times capital R. So we can look at AT as a chord that is equal to 2 times capital R and passes through the center of the semicircle. So any chord that is equal to 2 times capital R and passes through the center of the semicircle must be the diameter of this semicircle. Therefore, AT is the diameter of this semicircle. We join points A and D together by straight line. We join points A and D together by straight line. We join points D and T together by straight line. This way created peripheral angle ADT. Peripheral angle ADT rests on the diameter of this semicircle, and according to rule number 5, any peripheral angle that rests on the diameter of a circle or semicircle must be equal to 90 degrees. Here, peripheral angle A and B that rests on A and B, that is the diameter of the circle. Therefore, peripheral angle A and B equals to 90 degrees according to this rule, rule number 5. We can implement rule number 5 in our drawing, because in our drawing we have peripheral angle ADT that rests on AT, that is the diameter of the semicircle. Therefore, peripheral angle ADT equals to 90 degrees. We define this angle as alpha, this angle as beta, so then we focused on the right triangle, triangle ADT. In the right triangle, triangle ADT, this angle equals to 90 degrees, therefore the sum of the other two angles must be equal also to 90 degrees. So alpha plus beta must be equal to 90 degrees. From this equation we derive that beta equals to 90 degrees minus alpha and alpha equals to 90 degrees minus beta. We focus then in the right triangle, triangle ACD. The right triangle ACD, this angle equals to 90, this angle equals to beta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus beta, but 90 degrees minus beta equals to alpha. So we can substitute 90 degrees minus beta here by alpha. Likewise, in the right triangle CDT, this angle equals to 90 degrees. This angle equals to 90 degrees. This angle equals to alpha, therefore this angle must be equal to 90 degrees minus alpha. But we have already found out that 90 degrees minus alpha equals to beta, so we substitute 90 degrees minus alpha here by beta. Then we proved that the right triangle ACD is similar to the right triangle CDT. Why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to beta, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, therefore they are equal to each other. So we proved that those two right triangles are similar to each other according to angle similarity rule. From the fact that those two triangles are similar to each other, we conclude that the following relationship exists between their sides. We conclude that AC triangle ACD over CD equals to CD over CT again. We conclude that AC over CD equals to CD over CT. AC is capital R minus 2R, CD is 8, and CT is capital R plus 2R. Of course, multiply this equation and found out that 8 times 8 is 64. That is equal to capital R plus 2R times capital R minus 2R. We have already found out that capital R plus 2R times capital R minus 2R equals to capital R square minus 4R square. So, according to equation number 1, we found out that 64 equals to capital R square minus 4R square. What is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. I'll repeat again. The area of the green shape equals to the area of the quarter circle minus the area of the small circle. So the area of the quarter circle is pi times capital R square over 4. The area of the small circle is pi R square. Then we took pi over 4 as a common factor out of those two expressions. So inside the brackets we left only with capital R square minus 4R square. What we have already found out that capital R square minus 4R square is equal to 64, therefore we can substitute capital R square minus 4R square here by 64. We did it, and we got that the value of the green shape equals to pi over 4 times 64. 64 over 4 is 16. So in conclusion, we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. Okay, so in all three methods, we found out that the area of this green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. Okay, thank you very much.